Yes. Okay, so I think we can start. We have a good number of people here and we are online on YouTube. So first I want to say a few words. This is the first talk of this semester. We planned a whole season only with female researchers in order to honor women in science. So thank you very much, y'all, for being here today. And if you are new here and you want to receive the emails of the next talk, so please just subscribe to the form on our website, qpk.com. And that's it. So I hope you enjoy very much this season. And Nicole, thank you very much for accepting the invitation. And you may start whenever you're ready, okay?
Great. Thanks for the introduction and thanks for the invitation. I'm honored to be kicking off this season of talks.
Yeah, no problem.
I'm going to be talking about complexity. But complexity is a word that has many, many meanings. For instance, the Kolmogorov complexity of something is the minimal number of steps in an algorithm needed to create that thing. The computational complexity, many of us learned about from quantum computing class. Network complexity, we hear about a lot in the context of social networks and ecological networks. Incidentally, if you ever want anyone to talk about this kind of complexity in a quantum setting, then I recommend Logan Hilberry, who wrote a really great paper and has an exciting research program in that direction. There are even more definitions of complexity, but I'm going to talk about a type of complexity that is kind of generically named quantum complexity. It's come up in a number of settings, but I'm especially going to focus on what these high energy theorists, Adam Brown and Lenny Susskind, have had to say about it. By quantum complexity, I mean the difficulty of preparing some desired state from a simple tensor product, or the difficulty of taking such a state and uncomputing it to a simple tensor product. There are many different ways to quantify this type of complexity. For instance, if the system of interest is in a pure state, then we could say the state's complexity is the least number of 2-qubit gates that we need in any circuit to prepare the state. In the absence of noise, in order to prepare the all-zero state from the all-zero state, we don't have to do anything. So as an example, the complexity of the all-zero state could be said to be 0. According to a counting argument, the maximum possible complexity of any state is exponentially large in the number of qubits. This notion of quantum complexity has recently arisen in many different fields of quantum many-body physics. The application of it that led me into the study of it arose in holography. There is a concept of wormhole growth paradox, and it shows up in a certain correspondence between ADS, anti-de Sitter space, which is a certain geometry, a space-time geometry, and a CFT, a conformal field theory, which is a field theory on the boundary of this gravitational theory. In the gravitational space, there can be 2 black holes that are connected by a wormhole, and the wormhole's volume can grow linearly in time for a time that is exponentially large in the black hole size. There is some important time scale here that is exponentially large in the system size. So one might ask, what is the analog of that time scale in this conformal field theory picture? Because there is a duality between the anti-de Sitter space and the conformal field theory. You can look around at what might seem like reasonable candidates for the dual of this wormhole's volume. We can imagine measuring local observables of the CFT, or even complicated correlation functions that signal chaos. But these objects tend to evolve non-trivially only for much shorter times. They reach their equilibrium values much more quickly. The wormhole growth paradox is, how is it that there is a duality between these two pictures, but an important quantity in this picture changes non-trivially over a time scale much longer than any time scale that we seem to be able to find in this picture. A resolution was proposed in the complexity equals volume conjecture. According to this, the dual in the conformal field theory of this wormhole volume is the quantum complexity of this state of our conformal field theory. After this conjecture was put forth, complexity was actually conjectured to be dual to other things, such as a certain action of this space-time. And there's even a paper that's entitled Complexity Equals Anything. So complexity has established itself as a useful quantity to have in mind in this holographic ADS-CFT context. This notion of quantum complexity has also been useful in quantum computation, especially recently. For instance, we're probably all familiar with the paper that Google published that established what they claimed was a quantum advantage or supremacy experiment. Basically, the idea behind it is they had a quantum computer that prepared a state that was sufficiently complex so that sampling from that state was very difficult to do with a classical computer. Another relevant context is condensed matter. Here, we can consider some Hamiltonian that has a gap, a non-trivial gap between its ground state and its first excited state. That Hamiltonian could be in some interesting non-trivial topological phase, just if the ground state has a large enough complexity, a complexity that's greater than a constant in the system size. So quantum complexity has been establishing itself as a useful context across a useful concept across many body physics. But also something that I like to call uncomplexity is useful. By uncomplexity, I mean the greatest possible complexity minus the actual complexity. Why is this useful? The all zero states serves as input to a quantum computation. It serves as clean scrap paper, so it is useful, and it is very uncomplex. Because again, you need 0 steps to prepare the all zero state from the all zero state in the absence of noise. Since uncomplexity is useful, we could call it a resource. This way of thinking led Adam Brown and Lenny Susskind, who are, again, high energy theorists at Stanford, to propose that one might define a resource theory for quantum uncomplexity. Now, what is a resource theory? First, what are resources? I think of resources as things that are scarce and are valuable because they might be useful in tasks. For instance, if we have the resources of memory and time, then we can perform the task of solving computational problems. If we have a resource of money, then we can buy lab equipment, or if we're theorists, we can buy coffee. Often, when I ask quantum information scientists what they think of as resources, I'm told sleep, and granted, sleep is important for accomplishing just about anything. Since resources are so prevalent and useful and important, we might want a quantitative framework for measuring resources, comparing 2 different types of resources, and assessing the rates at which we interconvert or expend resources. Such a framework is offered by the resource theory framework. It's a mathematical tool developed in quantum information theory. A resource theory is a simple information theoretic model for any situation in which the operations that can be performed and the systems that can be accessed are restricted. The most famous resource theory that's been formalized is the resource theory for pure bipartite entanglement. In this, there are 2 agents, Alice and Bob. They are poor classical agents, kind of clumsy classical agents. They can't create controlled entanglement. They can only, at best, preserve entanglements, and they tend to decrease entanglement via the operations they can perform, which are local operations in classical communications. But every once in a while, they might receive a gift of a pure bipartite entanglement. We can, using the resource theory, check which states they can convert their given state into and which states they cannot. In a resource theory, again, some operations are allowed or easily performable. We approximate these as free or having no cost whatsoever. Everything else has some degree of scarcity, might be valuable. We could use it in a task. It's called a resource. We apply resource theories to formalize operational tasks, such as the distillation of high quality entanglement from a bunch of low quality entanglement. And we use resource theories to calculate the optimal efficiencies with which we can perform these tasks. The field of resource theories has exploded over the past several years. Resource theories have been defined for coherence relative to your favorite basis, thermodynamics, entanglement, resources for quantum computation, and more. I've had the pleasure and privilege of working with a wonderful team of people to define and analyze a resource theory for quantum uncomplexity, as was called for by those high energy theorists. Jonas Haferkamp, Philipp Feist, and Teja Kothakonda were recently in Jens Eisert's group in Berlin, and Anthony Munson is in my group in Maryland. The resource theories defined and analyzed in this paper, which I'll focus on, but this paper proves another conjecture by Adam Brown and Lenny Susskind, and it provides tools that we use in our resource theory. But here's where I'd like to go in the rest of this talk. First, I'll present the setup. Then I'll define this resource theory by specifying its free or allowed operations. I'll talk about two operational tasks, the extraction and expenditure of uncomplexity. Their efficiencies are quantified with an entropic quantity that I'll define called the complexity entropy. Then I'll introduce monotone statements, which we can prove about this resource theory. The monotone is a measure of the value in a resource. Value tends to decrease monotonically as systems are processed more and more. Then I'll talk about lots of opportunities for future work, and I'd be interested in hearing if you have any ideas. We're going to talk about a system of n qubits. Sometimes I'll denote the tensor product in this way. I'll denote by 0 the +1 eigenstates of the z component of the spin. And I'll denote by this bold-faced 1 the single qubit identity operator. We define a resource theory by specifying its set of free operations. The free operations in the resource theory of uncomplexity are built out of these building blocks called fuzzy gates. So this guy is wonderfully fuzzy, isn't he? Here's what happens when a fuzzy gate happens in our resource theory. We often, in talking about a resource theory, will have in mind some agent, such as an Alice or a Bob, who is performing the free operations. In our resource theory, an agent can pick any two of the qubits and target or try to perform any gate U in SU4, the set of two qubit gates. This choice of 2 is here just for convenience. If you prefer to think about k-body operations for some larger number k, then the results can be adapted. And also, if you prefer to work with discrete gate sets rather than continuous ones, then we can accommodate that preference. The agent might want to perform the gate U, but anytime we perform a gate in practice, the desired gate probably is not implemented because of noise. We model the noise like this. Let's denote by du tilde the Haar measure on the set of two qubit gates. It's loosely speaking the uniformly random measure on the set. More technically, it's the unique unitarily invariant measure on the group. The error is specified by some parameter epsilon. Denote by P any normalized probability distribution on the set of two qubit gates that has two properties. So this, well, in addition to what I'm about to describe. So this probability distribution depends on the target gates and the error parameter. The distribution is over the two qubit gates U tilde. Our noise can be modeled by any probability distribution that has these two properties. First, the distribution should encode how error is kind of in all directions, or of the set of the space of two qubit gates. So the probability distribution should be non-zero on an open set that contains the target gate. Second, this probability distribution should be non-zero only for gates that are epsilon close to the target gate. When a fuzzy gate is performed in the resource theory, it is selected randomly according to this distribution. That is a fuzzy gate. We said that the fuzzy gates are the building blocks of the free operations. We call the free operations, very creatively, fuzzy operations. Yes.
Can I ask a question?
Sure.
I mean, these, from what I understood, these probabilities should be non-zero only in the closure of the orbit defined by the element U.
Sorry, I'm having some trouble understanding you. Is there any chance that you have headphones or earbuds?
Yeah. Sorry.
Okay, that might be helpful.
Now, is it better?
I think that's better.
Okay, thanks. My question is this probability supposed to be non-zero only in the closure of the orbit of the set by the target gate?
So it should be non-zero just on gates that are epsilon close to the target gate, where epsilon is our error parameter. So
yeah, it's an arbitrary parameter. Yeah, I'm thinking about the closure of the orbit defined by the group.
What's really important here is that, okay, so the basic physical idea is that we have some, or the agent has some gate that they want to perform, and they end up performing a gate that's randomly selected from the gates nearby. What's really important for proofs later is that this probability distribution is absolutely continuous with respect to the Haar norm. So anywhere the Haar norm is zero, this probability distribution should be zero. And other than that, it's not too restricted.
Okay. Thank you.
No problem. The free operations we call fuzzy operations. The set of fuzzy operations is the set of all compositions of fuzzy gates. The reason for the distinction between fuzzy gates and fuzzy operations is small, technical, and unimportant. It's just the set of free operations in any resource theory should be closed under composition. And if you put two fuzzy gates together, you don't have necessarily a fuzzy gate. That's why we name this group of compositions. We could think of a state undergoing fuzzy gates as undergoing a stochastic trajectory of slightly random pure states. This picture I like to use because it's used a lot in this high energy theory literature that provided the motivation for this resource theory. They think about these stochastic trajectories a lot. And these random pure states aren't, even though the stochastic trajectory is motivated by the holographic literature, this notion of random pure states is not unknown in quantum information theory. For instance, there's a whole subfield of canonical typicality, which kind of combines quantum information theory with quantum thermodynamics, in which we talk about random pure states all the time. So according to this picture, we would start with some pure state psi. Then the agent would apply some slightly unknown gate U tilde 1, and then another slightly unknown gate, and so on. That the states would start out well known, but become slightly fuzzy, and then slightly fuzzier, and then slightly fuzzier. The agent might have some natural tolerance for the overall fuzziness permitted in the state. And so the agent might want to limit themselves to some maximum number of fuzzy gates. Or if you don't like thinking about stochastic trajectories of slightly random pure states, you could instead think about quantum channels. In this resource theory, no systems can be brought into the system of interest for free, and no systems can be discarded for free. This exclusion is a little bit unusual amongst resource theories, but there are other resource theories that have this property. Here's a motivation for instance, the lack of being able to tensor on any state for free. Tensoring on any state actually increases the overall uncomplexity. We can see that in a simple example. Suppose that we begin with a maximally complex state of n qubits. This is supposed to be pretty worthless for quantum computation. The complexity scales exponentially in the system size. Now, suppose that we tensor on what also seems like a pretty worthless state, another maximally complex state, this one of k qubits. Its complexity scales exponentially in k. The whole state has a complexity 2 to the n, that's like 2 to the n plus 2 to the k, because the number of gates we need to prepare the tensor product is the number we need to prepare the first factor plus the number of gates we need to prepare the second factor. However, the maximum possible complexity of the joint state is exponentially large in n plus k. So the gap between the maximum possible complexity and the actual complexity increases to this number minus this number from 0. So tensoring on even what we think of as a pretty worthless state does increase the uncomplexity. Uncomplexity is valuable, for instance, for quantum computation. So it shouldn't be free in our resource theory. So no tensoring on is free. This example is kind of a restatement of what was established many years ago in the one clean qubit model of quantum computation. Now that we've defined our resource theory, we can think about operational tasks that can be performed in it, the extraction and expenditure of uncomplexity. This extraction and expenditure are similar to the extraction and expenditure of work in thermodynamics, or the distillation and dilution of entanglement in the resource theory for entanglement. Let's look at the thermodynamic analogy a little more closely. In thermodynamics, we could have some compressed classical gas in a box. Since it's compressed, it has free energy, the capacity to perform work. So we can put a weight on top of the piston that caps this gas. This weight acts as a battery. It will absorb the capacity to perform work. We can allow the gas to expand against the piston, raising the weight, giving it gravitational potential energy, effectively charging the battery. We say that work is extracted into the battery. During work expenditure, we start with a lifted weight, a charged battery, and we can compress the gas to prepare a non-equilibrium state. It's been shown that in thermodynamics, outside of the conventional setting of an infinitely large system and only equilibrium initial and final states, the optimal work extractable from a system and the minimum work you need to prepare such a system can differ from each other. We're going to quantify our tasks' efficiencies using what we call the complexity entropy, which I'll define shortly. For background, ordinary entropies do not reflect uncomplexity. For instance, consider n qubits undergoing some chaotic random evolution. We can track the state across time t of qubit j. So we can check the state rho tj. Its von Neumann entropy is the entanglement entropy. The entanglement entropy can saturate in a time that's just polynomial in the system size, or depending on the model, even a constant time in the system size. In contrast, the complexity saturates in a time that's exponentially large in the system size. These are very different timescales. So the entropy tracks something very different from the complexity. However, we had an idea heavily inspired by this paper by various Caltech members. The basic idea is, suppose that you are given a very complex state, rho. Suppose that you, being a classical macroscopic observer, can perform just simple, somewhat local measurements. The outcomes of these measurements will look very random, as though the state were the maximally mixed state. So we might quantify the state's indistinguishability from the maximally mixed state in order to quantify the complexity. We choose to quantify indistinguishability using the hypothesis testing relative entropy from quantum information theory. Let's review that. Suppose that I give you a state and I tell you it's rho or sigma, but I don't tell you which. You need to perform a 2-outcome measurement and, based on the outcome, guess which state you received. In quantum information theory, we represent a general measurement with a positive operator valued measure, a POVM. It consists of a set of operators, M alpha, labeled by the classical outcomes alpha. Each of these operators is positive semi-definite, and the operators obey a normalization condition. For instance, if each of these M alphas is a projector, then the POVM reduces to a projector valued measure, which models the measurements that we learn about in undergrad quantum physics class. Our 2-outcome measurements will be represented by the sets Q and identity minus Q. Based on the outcome, we guess which state was most likely received. If we obtain the Q outcome, we should guess that the state was likely rho. If we obtain the identity minus the Q outcome, we should guess that the state was likely sigma. We can commit an error in 2 possible ways. First, we could receive rho, but obtain the identity minus Q outcome so that we would guess that the state is sigma. That's called a type 1 error. Very creatively, the other type of error is called a type 2 error. It happens if we obtain sigma, but the outcome we obtain from our measurement is associated with Q, so that we guess that the state was rho. We can intuitively understand these errors by replacing rho with no and sigma with yes. And suppose that the hypothesis test is between a patient's being not pregnant or pregnant. In this case, the answer is no, the patient is not pregnant, but apparently the doctor obtains the equivalent of the identity minus Q outcome and so guesses that the patient is pregnant. In a type 2 error, the patient is pregnant, so the answer should be yes, but the doctor obtains the Q outcome and so guesses no, the patient is not pregnant. We might have a natural tolerance for the maximum allowable probability of a type 1 error. That is, if we receive rho, then the probability of obtaining the wrong outcome, the identity minus Q outcome, should be small, should be upper bounded by 1 minus some small parameter eta of our choosing. Let's move pieces of this equation around to simplify it. That statement is equivalent to, if we receive rho, then we should have a high probability of obtaining the correct outcome. We should choose our measurements to satisfy this constraint on our type 1 error, and upon satisfying the constraint, set the type 2 error probability to the minimum possible value. Here's the mathematization of that. This is our constraint. This is the condition that the measurement operator is indeed a measurement operator. This is the probability of a type 2 error. If we obtain sigma, then we obtain the wrong Q outcome. And we would like to minimize this probability of a type 2 error. Again, this is a probability. when we do information theory, when we have probabilities, we like to stick them in logs with negative signs to create entropic quantities. So the hypothesis testing relative entropy between states rho and sigma is defined like this. This H is here for hypothesis testing. This eta specifies our tolerance for a type 1 error. And this probability in here is just the same probability as what we saw above. And here is the promised log a negative sign. We're going to take this hypothesis testing relative entropy and massage it until getting what we'll call the complexity entropy. We said that to quantify complexity, or uncomplexity rather, we should quantify a state's distinguishability from the maximally mixed state. So the state that we're comparing to, sigma, should be maximally mixed state. We can substitute in, we can simplify with a little bit of algebra, we can drop some unimportant constants, and less trivially, restrict the measurement operator Q to be somewhat simple. We do that in 2 steps. Oh, by the way, by what I mean by simple is that this measurement operator can be realized with a short circuit of up to some number R of gates, followed by a quite simple projective measurement. Here's some more detail. First, we'll specify a set of extremely simple measurement operators. We'll call them zero complexity measurement operators. We'll call this set M0. If one of these extremely simple measurement operators acts on a state, then each qubit, the jth qubit for all j, has one of 2 things happen to it. Either the qubit is projected onto the 0 states, or the qubit is not touched. It's acted on with an identity operator. Let's introduce a variable alpha sub j to specify what happens. If the projection happens, alpha sub j equals 1. If nothing happens, alpha sub j equals 0. Let's define notation such that if we raise this outer product to the 0 power, we get the identity operator. One of these extremely simple measurement operators has this form. It acts as a tensor product on all of the qubits from j equals 1 to j equals n. Each qubit, depending on the value of alpha j, is either projected or not touched. We'll call such an extremely simple measurement operator Q0. Q0 is in this set M0 of zero complexity measurement operators. Now let's build on that. Let's pick some number R, some non-negative integer. Let's say that before performing this extremely simple measurement, we're allowed to perform at most R 2-qubit gates, affecting some unitary use of R. How come? At the moment, we're just doing quantum information theory separately from the resource theory, but we're motivated by the resource theory to define this complexity entropy. And in the resource theory, we said that the agent can perform only fuzzy gates. And the agent might have some natural tolerance for how much fuzziness the overall state can have. So if the agent is smart, then they will limit the number of fuzzy gates that they perform so that the state doesn't become too fuzzy. That agent's natural impulse to limit the number of gates that they perform is the motivation for, in this pure definition of an entropic quantity, the specification of an R, an upper bound on the number of gates performable. So we're specifying a set of slightly complex measurement operators. And we can implement one of these measurement operators by performing a short circuit and then an extremely simple measurement. The affected measurement operator follows from conjugating this extremely simple measurement operator with the little unitary. This complexity restricted measurement operator I'll call Q. It belongs in the set M sub R of fairly simple measurement operators. We can now define the complexity entropy. This complexity entropy has this C here for complexity. It's parameterized by R, the maximum number of gates in the fairly simple measurement operators. It's also parameterized by this tolerance eta for a type 1 error. And this complexity entropy is intended to tell us how complex a state rho is. Here we have the trace of a complexity restricted measurement operator. This minimization is over the complexity restricted measurement operators that satisfy the type 1 error probability tolerance. This error parameter here can be chosen in accordance with the agent's personal preferences. How does this complexity entropy behave? We can get some intuition about it by considering two extremes. First, suppose that we are trying to distinguish a given state rho from the maximally mixed state using just a short circuit and a very simple measurement. Suppose that the number of gates that we can perform to try to distinguish this state from the maximally mixed state is pretty large, at least the number of gates that we needed to prepare the original state in the first place. By the way, for the sake of elaborating on these two simple extremes, I'm going to suppose that this rho is a pure state that is the outer product of psi with itself. In this case, if the number of gates performable is large, then the complexity entropy is small. It's actually 0. In the second extreme, we suppose that the number of gates performable is much less than the number of gates we need to prepare the state in the first place. Now the complexity entropy is large. It can be up to the system size. Does anyone have questions about the complexity entropy?
Oh, I actually have. I didn't get a physical picture behind of these because I know some measures of complexity, like computational complexity, which basically measures the minimal number of gates that you needed to apply to a system in order to prepare the stage, or Kolmogorov complexity, which measures the rate at which you lose information in classical physics.
This is
But
measuring.
I don't understand exactly what this is measuring.
But this is measuring. Suppose that you're given a state rho, and you can perform only pretty simple measurements on it. Measurements that consist of just a few gates and a really, really simple measurement projection. Then how accurately can you distinguish this state from the maximally mixed state? Because if this state is really, really complex, so that to prepare it from the all zero state, say, you would have to perform lots and lots of gates, then the state is probably pretty entangled. And so if you can perform only a simple kind of local measurement, then you're just going to get really random looking outcomes. So it'll look locally as though this system is really close to maximally mixed. This complexity entropy is measuring if you can probe the system only with limited computational power, then how close does it look to maximally mixed?
Okay, let me think about it. Let us suppose that I have a system that I can only measure energy. I cannot perform any other measurements. So just projection on the energy eigenbasis. If I let the system to evolve, the system will develop coherence between the energy eigenstates. If I'm not able to measure anything else than energy, then the system will look like completely mixed for me in a very short time. Is that thing that is measuring here?
Here we're thinking, or the kind of ideal system that we have in mind is a many-body system with pretty generic interactions. So its Hamiltonian will probably be non-integrable, and measuring the energy would be really, really, really difficult. So that would require a lot of computational power. You'd effectively have to, before your extremely simple measurement, perform a quite sizable circuit. And so what you're telling me is basically you're supposing that R is extremely large. If you can measure the energy.
Okay, I see what you mean.
I'm also going to show an application of this in an operational task. So maybe that will provide an extra physical insight.
Okay, thanks very much.
Sure. Speaking of which, there are operational tasks that we can define in this resource theory. The complexity entropy quantifies the efficiencies with which we can perform these tasks. I'm going to illustrate with the extraction of uncomplexity from a given state. This is analogous to the charging of a battery in thermodynamics. Let's define the task of uncomplexity extraction in this resource theory. Suppose that the agent in the resource theory receives an arbitrary n-qubit state rho, which we can represent with these wires. The agent can perform up to R fuzzy gates because, remember, they probably have some natural tolerance for how fuzzy the overall state can get, so they shouldn't perform too many fuzzy gates. Then the agent can pick W of the qubits, and those W qubits have to end up delta close to the tensor product of zeros, wherein the delta closeness is measured by the trace distance. So for some given tolerance of closeness, the trace distance between the final state of these W qubits and the L0 state has to be at most delta. We then say that the agent has extracted W totally uncomplex qubits with a delta approximation. We need to find out the greatest possible value of W, how many qubits can be extracted. We quantify the W with this theorem about uncomplexity extraction. Suppose that the tolerance for closeness to the L0 state is at least the number of gates performable times the fuzziness parameter. Then, for every value of a parameter in some range specified by these three parameters, it is possible to extract a number of qubits, that's the total system size minus the complexity entropy, such that those extracted qubits are close to the L0 state, delta close in trace distance. Also, if you ever succeed in extracting W qubits that are close to the L0 state, then the number of qubits that you extract is certainly upper bounded by the system size minus the complexity entropy. But here we have an achievability statement and an optimality statement. The proof relies on the triangle inequality, properties of projectors, and the ordinary quantum information theory. Does anybody have questions about that? Okay. Then we could briefly talk about monotones. Every resource theory features monotones. A monotone is a function of a state. It quantifies how much resourcefulness that state has according to some measure. These monotones tend to decrease monotonically under free operations. So monotones generalize the free energy of thermodynamics. Consider a non-equilibrium system that is thermalizing. Its free energy decreases monotonically. And so the system's ability to provide work decreases monotonically. So the free energy specifies how much value the state has in thermodynamics. If F denotes any monotone, E denotes any free operation, and rho denotes any state in a resource theory, then this inequality holds. Why consider different monotones? One reason is different monotones specify a state's value in different operational tasks. We already saw the example in thermodynamics of how the work you can extract from a system and the work that you need to prepare a system can differ from each other outside of conventional thermodynamic settings. Or as Frodo might tell us, there is no one monotone to rule them all. Which monotone is relevant depends on the setting. We did prove that there are monotones in the resource theory of uncomplexity. As a caveat, bounding how uncomplexity changes under evolution is extremely difficult. This task has been worked on for many, many years. For that reason, our monotone results hold just in certain regimes. We were able to use this tool in this paper that I mentioned earlier. In it, we prove a different conjecture by our holographic friends Adam Brown and Nicole Susskind. Also, this conjecture was inspired by the black hole information paradox. In order to formalize this conjecture, let me define the exact circuit complexity as the least number of 2-qubit gates that we need to prepare some pure state from the all-zero state. We proved that this exact circuit complexity, under a pretty generic random unitary circuit evolution, grows linearly in time for a time exponentially large in the system size, similarly to the volume of this wormhole. We used completely different tools than are usually used in the complexity literature, namely algebraic geometry and differential topology. This proof technique is really, Jonas deserves credit for this proof technique. It was kind of out of left field because most people don't use this kind of mathematics in quantum complexity. So we were quite proud of ourselves for proving this conjecture using these new tools. However, after we proved this conjecture, then someone came along and used our framework and managed to prove that conjecture twice in just 2 pages, whereas we had spent a decent number of pages on proving this. So that was a great source of humility. So to present one of the monotones, I'll present a little bit of background. A very common type of circuit is a brickwork circuit. Consider a set of n qubits evolving under these 2-qubit gates that have this staggered geometry to them. We will focus on brickwork circuits that have periodic boundary conditions. So in the 2nd layer, 4th layer, and so on, qubit 1 and qubit n are connected by a gate. Let's define the brickwork complexity of a pure state psi as the least number of gates needed in any brickwork circuit that can prepare the state. The brickwork uncomplexity is just the maximum possible complexity minus the actual brickwork complexity. We proved that the brickwork uncomplexity is a monotone in the resource theory. I'll first state the theorem and then draw it out. Let psi denote your favorite n-qubit pure state. The state has a brickwork uncomplexity that decreases monotonically under every brickwork circuit that consists of fuzzy gates and consists of at least a number of layers equal to the system size, except in an extremely small set, a measure 0 set of experiments formed from randomly selecting psi and randomly sampling the circuit. Let me draw out that theorem. We're interested in a set of n qubits. Suppose that it's prepared in a pure state psi. This state has some brickwork uncomplexity. Suppose that the state undergoes some unitary of fuzzy gates formed from fuzzy gates. Suppose that this circuit consists of at least n layers. The output is some other state. That state will have some brickwork uncomplexity of its own. That brickwork uncomplexity is less than the initial brickwork uncomplexity with probability 1. Does anyone have questions about that theorem? Okay. We also conjecture the existence of another natural monotone. We've seen the complexity entropy If we subtract it from its maximum possible value, we get a complexity negentropy. We expect this quantity to be a monotone fairly generally for a few reasons. First, as we saw, the complexity entropy quantifies the efficiencies with which we can perform operational tasks. So it's like an entropy in thermodynamics, and so like the free energy in thermodynamics. We should expect it to decline to change monotonically. Also, we can prove that this quantity is a monotone in two cases: when this parameter, which specifies our error tolerance, has an extreme value. How come? Because in this case, we can apply that algebraic geometry toolkit introduced in the earlier paper. We conjecture that for any n-qubit state rho, the complexity entropy decreases monotonically under all fuzzy operations, and the statements would hold for all r, which is the parameter specifying this complexity entropy. So all number of gates that you could use to distinguish your state from the maximally mixed state, as long as this tolerance parameter eta is large enough as a function of the fuzziness parameter epsilon. That's our conjecture. And it leads to the opportunities for future work. First, it would be useful to prove that conjecture. Second, it would be nice to study the complexity entropy in its own rights as a quantum information theoretic quantity. Also, we showed that this complexity entropy quantifies the efficiencies of tasks performable by an agent that's computationally restricted, that would like to perform no more than some number of gates. Maybe the complexity entropy can quantify the efficiencies of other tasks undertaken by computationally restricted agents. This resource theory was motivated by high energy theory. So we really had high energy theory in mind, but it is one resource theory and a broad landscape of resource theories. It'd be nice to study more of its resource theoretic properties and see where it is in this landscape. There is another resource theory that also quantifies the difficulty of preparing a state, similarly to our resource theory. But that resource theory is called the resource theory for magic, or quantum computation that involves non-stabilizer operations. I can say more about that if you're interested. It would be interesting to put together these two resource theories for how difficult it is to prepare a state and make one overarching unified resource theory. Since high energy theory motivated our work, it would be good to take this tool that was motivated by high energy theorists and apply it to high energy theory, find applications to holography and other spheres of many-body physics. For instance, it'd be great to find some story about, say, Alice falling into a black hole with qubits and recast part of that problem in terms of uncomplexity extraction or expenditure so that we could use tools from the resource theory. And since we're close to the end of the hour, I'm going to skip that opportunity and head straight to the summary. We saw that the notion of quantum complexity has been a useful concept in a number of spheres of many-body quantum physics. We talked about the resource theory framework as a toolkit for making statements about what's possible and what's impossible and about operational tasks. Our holographic friends called for the construction of a resource theory of quantum uncomplexity. We met that challenge by defining a resource theory in terms of fuzzy operations. We specified tasks whose efficiencies were quantified in terms of this complexity entropy. In particular, we saw the example of uncomplexity extraction. We talked about monotones, functions that measure a state's value and decrease monotonically under the free operations. And so that much is left to be done. Thanks for your attention.
Thank you, Nicole. Okay, so now we open to questions.
Hi, I have a question.
Yeah, please.
Hello, can you hear me, Nicole?
Yes, yes, we can hear you.
I follow everything because my connection is really unstable today. I mean, as usual, actually. So, I mean, I just have a kind of general, maybe naive question, because I mean, it seems that at the end, I mean, you're just trying to I mean, instead of how much complexity you have in operations, how much you still could achieve at most, no? Isn't like just making a, I mean, it's not like just subtracting an amount, no, not just changing the adding something in this, because that's, I mean, is it in some sense, how can you relate this uncomplexity with complex of the state at all? Is it supposed to be expect to have a relation between these two things? I'm not sure if I make myself clear.
Sorry, I'm having some trouble understanding the question.
So, so it seems, I mean, so you're, I mean, I have maybe a question is what's the advantage or the difference between uncomplexity and complexity at the end? Because it seems kind of similar, no? Because uncomplexity are just not talking about the amount of complexity you have there, but the amount you could achieve, no? At most, is that correct?
It sounds like the question is, what's the difference between complexity and uncomplexity? We think of uncomplexity as closeness to simple tensor products, and we choose to distinguish the all zero state since that's by convention maximally useful for quantum computation. So we think of uncomplexity as basically closeness to the all zero state in some operational sense, as in it's easy to get to the all zero state from the given state, or it's easy to prepare our state from the all zero state. And we think of complexity as basically the opposite. So distance or being far from the all zero state.
Okay. And I mean, can you think, I mean, as another question, because the little know about complexity, I mean, I know that many people thinking about entropy as a measure of disorder and complexity somehow, but we know it's not completely true. No, I mean, many instances entropy and what we call complexity are not the same thing. And even classically, this is I understood this is an open problem. No, is there a classical sense of complexity also, and how would be? I mean, what would be the notion?
So about the entropies, yes, the typical entropies, for instance, the entanglement entropy or the entropy of the entire system, those don't track the complexity. For instance, under some random evolutions, the entanglement entropy or the entropy of the full system tend to equilibrate over a relatively short time scale, whereas the complexity saturates only after a time that's exponentially large in the system size. So usually they do measure different things. That's why we had to go through this whole construction process to come up with a complexity entropy, which we claim tells us something about complexity using a very special entropic quantity. As for classical complexity, you can ask analogous questions about classical computation and ask, say, what is the least number of classical gates needed to prepare something?
Okay. Thank you.
Yeah, any more questions?
Well, I have several actually, but of course we don't have time to do this. I'm still trying to understand the physical meaning of this uncomplexity measure.
Do you mean the complexity entropy?
Yeah, the complexity entropy. Is there a classical a limit for this quantity?
I'm not sure how you'd get a classical limit.
Yeah, I was thinking about this, and it looks like very hard to go for
that's
this.
Possible.
Yeah, because in classical physics, I do understand complexity. I mean, in terms of algorithmic complexity or Kolmogorov complexity, which can be put to one in terms of the other.
This
But,
is a different type of complexity.
yeah, it's a different type. That's why I'm trying to understand.
Mhm.
I mean, what's the difference, actual difference between these things?
See, so the Kolmogorov complexity, for instance, is the size of the smallest algorithm needed to prepare something. And if you can get a very random product by specifying just a really simple set of instructions, like flip a coin a lot of times, whereas here's something very random looking would be a very complex states imagine a state that to be prepared requires first a null zero state and then many, many, many gates on top of that. If we performed only simple measurements on it, then the outcomes would look very, very random. So
Okay.
also this has a lot of randomness, but we would say that it has a high complexity because it involves a lot of, or preparing the state requires a lot of gates.
Yeah, I understood that is deeply related with the number of gates that you need to actually prepare the system.
Mhm.
And you have the restriction that you are only able to perform some measurements.
Mhm.
Okay, and mathematically I understood everything you said. I'm just trying to get the physical picture. But I'm gonna read your paper. It's
okay. Or for
yes.
instance, suppose that you're given a state rho and you are trying to characterize its complexity using the complexity entropy. Then you could fix the error parameter eta. And you could say, okay, at first, suppose that I can perform only r equals 1 gates in my measurement. Then the outcomes are going to look really, really random. And the complexity entropy will be maximal. Now, suppose that we increase r to being linear in the system size. And maybe still the complexity entropy is very large, maybe it's maximum possible value. So again, the state looks very, very random. And we keep increasing r, and eventually we will hit an r circuit size such that we can distinguish between this given state and the maximally mixed state using our complexity restricted measurement. Then we would say that this is a good quantification for how complex the state is.
Okay, I see. Now I see what you mean. Oh, now I got. Oh, okay. Many thanks. Now I understood.
Great.
Now I see what this quantity is measuring. Oh, thank you very much. This is nice, actually. It's very nice.
And if you have any ideas about it, then we're very open to hearing.
Yeah. Do we have more questions?
No, that's the last one. Have you considered relating these restrictions with some sort of coarse grading in quantum mechanics?
The idea of coarse grading has come up, but we haven't necessarily done a whole lot of it. And did you have any particular idea in mind?
No. I just came into my mind now that I really understood what you said. So it looks like the restriction could be mapped into some sort of coarse grading, which are always problematic in quantum mechanics.
Yeah, it would be especially satisfying if there was some kind of maybe a normalization group or something that could be associated with this. Yeah, that would be really nice.
Okay, many thanks for your talk and for accepting Pedro's invitation.
Yes, thanks very much for hosting me.
Yeah. Okay. So
Pedro, I'm satisfied.
Okay. If there are further questions, feel free to email.
Okay. All right. So no questions on YouTube. Okay, so Nicole, I want to thank you again for accepting the invitation. It was
Thanks for having me.
Really nice.
It's been a pleasure.
Yeah, thank you very much. And that's it. So see you guys on 2 weeks, and bye-bye. Have a good day.
Thanks.
Yeah, see you.
Bye-bye, good day, and good night to other people.
See you guys. Have a good day.